So continuing off the previous video, now let's calculate the double integral of 6x squared y cubed minus 5y to the fourth dA. And this time the double integral is described by the region R. And the region R is in set notation for all xy coordinates such that the x values range from 0 to 3 and the y values range from 0 to 1. So what we have to do here is basically turn this double integral into an iterated integral and then evaluate it. So if I were to go ahead and rewrite the integral, we get the double integral of 6x squared y cubed minus 5y to the fourth. Now I'm going to not write the dA right now, I'm going to skip that and come back to it later. And so notice that we have to have one integral that contains the x bounds and one integral that contains the y bounds. Now you might wonder, well, since x is from 0 to 3, should I put that on the outer integral or the inner integral? And since y is from 0 to 1, should I put from 0 to 1 on the outer integral or the inner integral? Well, this is where Fubini's theorem is useful, because if f, the function, the multivariable function here, is continuous on the given region, then we can say that the integral, or the double integral, the outer one from c to d and the inner one from a to b, of some multivariable function f of x, y. And so remember that dA is the same thing as dx times dy or dy times dx. Since a and b are associated with x bounds, we'll put dx on the inside. Since c and d are associated with y bounds, we'll put dy on the outside. And so Fubini's theorem states that if you switch the order of dy dx and you switch the order of the integrals, you'll get the exact same answer. So this is basically equal to the double integral, the outer one this time from a to b and the inner one from c to d, of the same multivariable function. This time dy is on the inside and dx is on the outside. Remember, you have to switch both the dy dx and the integral. And once again, also remember the function has to be continuous on the given region R. And so to double check, no matter what values you plug in for x between 0 and 3, and no matter what values you plug in for y between 0 and 1 into the original function, you will get always a real answer. So yes, the function is continuous. So we can use Fubini's theorem. And so if I go back to the double integral here, let's just go ahead and put the x bounds first on the inner integral, so from 0 to 3, and the y bounds on the outer integral. So if x bounds are on the inside, I have to put dx first. And if the y bounds from 0 to 1 on the outside, I have to put dy outside. And now we can go ahead and solve the iterated integral. So I'm going to go ahead and write down the inner integral first. So from 0 to 3 of 6x squared y cubed minus 5y to the fourth. Since we are integrating with respect to x is going to be treated as a variable and y is a constant. So the integral of 6x cubed y cubed, remember 6 and y cubed are both constants, so the integral of x squared is x cubed over 3. So we get 6 times x cubed over 3 times the constant y cubed minus the integral of 5y to the fourth, which is 5y to the fourth times x, because remember 5y to the fourth is a constant and we're integrating with respect to x. So now we can go ahead and evaluate from the bounds, the x bounds of 0 to 3. So remember, I'm going to plug these bounds in for only x, because they are x bounds. So when I do that, I'll get 6 times 3 cubed, so 6 times 27 over 3 times y cubed minus, when I plug in 3 for x, we get 5 times 3, 15, y to the fourth, minus, when I plug in 0, we'll just get 0 minus 0. So that will cancel. So when I simplify this, 6 over 3 is 2, so 2 times 27 is 54. So we get 54, let me rewrite that once again, 54y cubed minus 15y to the fourth. So now that we have found what the inner integral is, let's go ahead and now put it inside the outer integral. So we're going to put the integral from 0 to 1 of 54y cubed minus 15y to the fourth dy. Now we're going to integrate with respect to y. So the integral of 54y cubed is 54y to the fourth over 4 minus the integral of 15y to the fourth, 15y to the fifth over 5. Now 54 over 4 can be simplified into 27 over 2. So you get 27 over 2 y to the fourth minus 15 over 5, which simplifies to 3. So we get 3 times y to the fifth. Let's go ahead and now evaluate that from the y bounds of 0 to 1. So when I do that, we get 27 over 2 times 1 to the fourth, so just 27 over 2, minus 3 times 1 to the fifth, just 3, minus when I plug in 0, we'll get 0 minus 0, so that will cancel. So now we get 27 over 2 minus 3, which I can rewrite as 6 over 2. So then 27 minus 6 is 21, so the final answer is 21 over 2. So for number 2, we have the double integral of xy squared over x squared plus 1 dA, and it's described by the region R in set notation for all xy ordered pairs, such that the x values range from 0 to 1, and the y values range from -3 to 3. So once again, we're just going to set it up like an iterated integral. So if I rewrite the double integral here of xy squared over x squared plus 1, so this time, or in the previous problem, we put the x bounds on the inside integral. This time, let's go ahead and put the y bounds on the inside integral and switch it up. So we're going to go from -3 to 3. So this time dy is going to be on the inside, since we're looking at y bounds in the inside integral. The outer integral is going to go from 0 to 1, so dx will be on the outside. So if I go ahead and rewrite the first integral here, we have the integral, or the inside integral, from -3 to 3 of xy squared over x squared plus 1 dy. Now since we are integrating with respect to y, everything but the y variable we treat it as a constant. So basically what we can do here is take this entire x over x squared plus 1 and put that outside of the integral, since it is a constant in this case. So we have x over x squared plus 1 times the integral from -3 to 3 of just y squared dy. So the integral of y squared is y cubed over 3. And if we go ahead and evaluate that from -3 to 3, let's go ahead and plug in 3 first. So we'll get 3 cubed, which is 27 over 3, which is 9. Minus, when I plug in -3, we'll get -3 cubed, or in other words, -27 over 3, which is -9. So minus a -9 would be plus 9. So then we get 18. Don't forget that we do have this x over x squared plus 1 outside of the integral. So now we can go ahead and multiply that by 18. So we're left with 18x over x squared plus 1. So now we can go ahead and put what we found for the inside integral inside of the outer integral. So now the integral from 0 to 1 of 18x over x squared plus 1 dx. So now we're going to integrate with respect to x. So now I'm going to go ahead and put this 18 outside of the integral. This is a constant. So 18 times the integral from 0 to 1 of x over x squared plus 1. And notice it's just a simple u substitution problem. So if u equals x squared plus 1, du is then going to equal 2x dx. So then if we solve for dx, dx is going to be du over 2x. So if I go ahead and plug that in for dx and make x squared plus 1 my u, we will then get the 18 times the integral from 0 to 1 of x over u times dx, which is du over 2x. So notice the 1/2 is a constant, so we can come outside of the integral. So 18 times 1/2, or 18 over 2, is 9. Notice the x's will cancel as well. So we'll get 9 times the integral from 0 to 1 of 1 over u du. Now the integral of 1 over u is just the natural log of the absolute value of u. And don't forget we have a 9 on the outside, so 9 times the natural log of absolute value of u. Remember we made u equal to x squared plus 1, so we can go ahead and replace that back. So now let's go ahead and evaluate it from 0 to 1. So when I do that, we'll get 9 times the natural log of 1 squared plus 1, that's 2, minus, when I plug in 0, 9 times the natural log of 0 plus 1, which is 1. Natural log of 1 is 0, so that will cancel, and so we're left with 9 times the natural log of 2. So for number 3, we have the double integral of x sine of x plus y dA, and it's described by the region R, which in bracket notation, the x values go from 0 to pi over 6, and the y values go from 0 to pi over 3. So just realize that if it's in this kind of bracket notation, the first one refers to the range of x values, the second one refers to the range of y values. So if I go ahead and rewrite the integral, we get the integral of x times sine of x plus y. So let's go ahead and just put the x bounds first on the inside integral, so from 0 to pi over 6, and then put the y bounds on the outer integral from 0 to pi over 3. So now if I rewrite the inside integral from 0 to pi over 6 of x times sine of x plus y dx. Now realize that since we're integrating with respect to x, once again x is going to be the variable, y is going to be the constant in this case. So how could you integrate this? Well, remember when we integrated x times sine of x, we had to use integration by parts. So this is the same exact rule here. We still have to use integration by parts to integrate this. So remember, when we use integration by parts, we need a u, we need dv, and then we need the plus or minus sign chart. So for u, let's just pick u to be x. So, and then dv will then be sine of x plus y. So on the u column we derive, on the dv column we integrate. So the derivative of x is just 1, and the derivative of 1 is 0. Now the integral of sine of x plus y. Now remember, we're integrating with respect to x only, so y is going to be a constant. So the integral of sine of x plus y is negative cosine of x plus y. And the integral of negative cosine is just negative sine of x plus y. And then we obviously start with the plus and go minus and then plus. So now the next step is obviously just multiply and then use the sign, and then multiply and then use the sign. So we have x times negative cosine of x plus y, which is going to be negative x times cosine of x plus y. The next sign is a negative, so then we have minus another negative. So minus a negative would be positive here, plus 1 times sine of x plus y, which is just sine of x plus y. And then we have plus, and now we're going to put the last row in an integral. So we have plus the integral of negative sine of x plus y times 0. Now since it's times 0, we just have 0, and the integral of 0 is 0, so that just cancels. So this is left as the integral of x times sine of x plus y. So now we can go ahead and evaluate from the bounds, from the x bounds of 0 to pi over 6. So then when I plug in pi over 6 for x, we'll get negative pi over 6 times cosine of pi over 6 plus y. And we have plus sine of pi over 6 plus y. Go ahead and put those in parentheses. I'll actually move this down a little bit. Minus when I plug in 0 for x. So then we'll get negative 0 times cosine, well that should be 0. And then we have positive sine of 0 plus y, which is sine of y. So now I can go ahead and rewrite it as negative pi over 6 times cosine of pi over 6 plus y plus sine of pi over 6 plus y minus sine of y. So now I can put this under the outer integral. So now the integral from 0 to pi over 3 of dy. Now if you go ahead and take the integral of this first term here, negative pi over 6 cosine of pi over 6 plus y. Now pi over 6 is just a constant, so I can put that outside of the integral. So we basically have, or I can put negative pi over 6 outside the integral as well, of cosine of pi over 6 plus y. Now cosine of a constant plus y, the variable, when we're integrating with respect to y, the integral is just going to be sine of pi over 6 plus y. So negative pi over 6 times sine of pi over 6 plus y. And so the integral of sine of pi over 6 plus y is just going to be negative cosine of pi over 6 plus y. Then the integral of negative sine of y is just going to be positive cosine of y. Let's go ahead and evaluate that from 0 to pi over 3. Those are the y bounds once again. So then when I plug in pi over 3 for y, we'll get negative pi over 6 sine of pi over 6 plus pi over 3. Now pi over 6 plus pi over 3, I can rewrite pi over 3 as 2 pi over 6. So then 2 pi plus pi is 3 pi over 6, which can be simplified to pi over 2. So I will rewrite sine of pi over 6 plus pi over 3 as sine of pi over 2 minus cosine of pi over 6 plus pi over 3, once again is simply pi over 2. And then we have plus cosine of pi over 3. Now minus, when I plug in 0 for y, then we'll get negative pi over 6 cosine of pi over 6 plus 0, just pi over 6, minus cosine of pi over 6 plus 0, just pi over 6. And then we have plus cosine of 0, which is 1. Now, cosine of pi over 2 is 0, so that's out. Sine of pi over 2 is 1. 1 times negative pi over 6 is negative pi over 6. And we have plus cosine of pi over 3. And so cosine of pi over 3, or cosine of 60 degrees, is going to be 1/2. So we have plus 1/2 minus, now we have sine of pi over 6, which is also 1/2. 1/2 times negative pi over 6 is negative pi over 12. Minus cosine of pi over 6. Cosine of pi over 6, or cosine of 30 degrees, is a negative square root of 3 over 2. And then we have plus 1. Now if I go ahead and distribute the negative over to inside the parentheses, we'll get negative pi over 6 plus 1/2. And now distributing the negative, we'll get positive pi over 12 plus square root of 3 over 2 minus 1. So now 1/2 minus 1 is negative 1/2. I'll just go ahead and group that with the positive square root of 3 over 2. So we get square root of 3 over 2 minus 1/2. And I'll go ahead and group these two together. So then we have negative pi over 6 plus pi over 12. Now pi over 6 can be rewritten as 2 pi over 12. So negative 2 pi plus pi is negative pi. So then we get negative pi over 12. And so we have square root of 3 over 2 minus 1/2 minus pi over 12. So then I can go ahead and combine these two fractions. So we get the square root of 3 minus 1 over 2 minus pi over 12. And that's the final answer. So now for number 4, we have the double integral of xy e to the x squared y dA. For the region R, the x values range from 0 to 1, and the y values range from 0 to 2. So if I go ahead and rewrite the double integral here of xy e to the x squared y, now I'm going to go ahead and actually choose the x bounds to be on the inside integral, so from 0 to 1, and the y bounds on the outside, so from 0 to 2. And the reason why I do that is because now I have turned it into a simple u substitution problem. So if I go ahead and rewrite the inside integral from 0 to 1 of x times y times e to the x squared y times dx, I'm just going to go ahead and make u equal to x squared times y. So if u equals x squared y, remember we're going to derive with respect to x. So then du, if y is a constant, is going to be 2xy times dx. And so if we solve for dx, dx is going to be du over 2xy. Now if I go ahead and plug that into back to the integral, we get the integral from 0 to 1 of x times y times e to the x squared y, which we made to be u. So we have e to the u times dx, which is equal to du over 2xy. Notice the x and y's will both cancel. 1/2 is a constant, so it can come outside of the integral. So we'll get 1/2 times the integral from 0 to 1 of e to the u du. So now the integral of e to the u is just e to the u. So we have 1/2 times e to the u. Now u is x squared times y, so we can go ahead and replace that back in. So e to the x squared times y. And then we're going to go ahead and evaluate from the x bounds of 0 to 1. So if I go ahead and plug in 1 for x, we'll get 1/2 e to the 1 squared times y, just y, minus when I plug in 0, we get 1/2 times e to the 0. E to the 0 is 1, 1 times 1/2 is 1/2. So we'll get e to the y over 2 minus 1 over 2. So I'll just go ahead and rewrite it as 1/2 times e to the y minus 1. So now that I have found the inside integral, let's go ahead and solve for the outside integral. Integral from 0 to 2 of the inside times dy. Since 1/2 is a constant, I can go ahead and take that outside the integral. So we get 1/2 times the integral from 0 to 2 of e to the y minus 1 dy. And so the integral of e to the y is just e to the y. So we get e to the y and then minus the integral of 1, which is just y, if we're integrating with respect to y. And don't forget, we do have that 1/2 on the outside as a constant, so go ahead and multiply by that. And then we're going to evaluate from the y bounds of 0 to 2. So when I evaluate, we get 1/2 times, if I go ahead and plug in 2 for y, we'll get e squared minus 2, and then minus, when I plug in 0 for y, we'll get e to the 0, which is 1, minus 0. 1 minus 0 is obviously 1. So then we get 1/2 times e squared minus 2 minus 1. So then negative 2 minus 1 is negative 3. So we'll get 1/2 times e squared minus 3. And that's the final answer.